So for the fourth experiment for my power electronics subject, it is entitled Half-Wave Rectifier with RL Source Load and Inductor Source Load. So for the objectives, first is to simulate the half-wave rectifier with RL source load using PSPI software. Next, to utilize the software to observe the behavior of half-wave rectifier with RL source load and to determine the power quantities using PSPI software. So for the procedures, the part 1 is to construct the RL source load circuit. So to do that, we have to open PSpice and create the circuit shown in figure 3.5a. So this is the figure. This is a AC source diode, a resistor, an inductor, this is the RL circuit, and a DC voltage source. So here are the values that we would be changing later on the circuit. So first we need to open the OrCAD app. Click on Start and type OrCAD. Click the application. Wait for it to load. After the application has loaded completely, click on File. Here, click on New Project and type the project name. So for my case, I will put experiment 4 and click OK. After that, click on Create a Blank Project. Next, we need to construct the circuit. So click Place. Let's search for the diode. Here at the PSpice part switch, let's type D break. So click on diode breakout device, D break. Double click and place it here. After that, what we're going to do is construct the circuit. So we need the resistor, inductor, and the sources. So to do that, click on place PSpice component, inductor, and the other components, the resistor, I've already put them, and the source. And we're going to search for the voltage sign. So we can include the transient voltage source here. Next, we can wire the circuit. So just press on W so we can wire. Connect them as according to figure in the experiment. And also, of course, we need to place a ground. Next is to change the values of the components in the circuit. The resistor is 2, the inductor is 20 millihenries, the voltage DC is 100 volts DC, and the D break is just the D break. And here the value for the voltage amplitude is the voltage multiplied to the square root of 2, which will give us a value of 311.127. Next, the value of the frequency is 60 Hertz. So let's click on here and put here 60, and the voltage off is 0 and the AC is 0. Next, we'll change the name of the components. This is DAC and DDC, just for future references when we trace our waveforms. So the next thing that we need to do is to add a simulation profile. So click on here and I'm gonna name it experiment 4 part 1 and click create. After that, what we should do is just wait for the application to load. A pop-up window should appear, and here we're going to set the runtime in time domain transient type. This is the type of our analysis. So the runtime, we're going to change this to 16.67 milliseconds, and for the maximum time size seconds, that's 10 ms, sorry, and we're going to click apply and okay. And then again, we're going to wait, and once we click play here, a pop-up window should appear again, and we can see this where we can add our traces. So to add the trace, we should uh, perform transient analysis and display this expression. So what I'm going to do, I'm just going to copy here, and we're going to add this here when we add our trace. We're going to click on trace, add trace, and paste. Okay, so here, as you can see, so as you can observe here, this is the waveform of the average power absorbed by the resistor. So in order to see the peak value and the average power values, what we need to do is right click and click on cursor on, and if we are to put the cursor at the very peak of the voltage value, we can of the waveform rather, we can observe that the peak value of the average power has a value of 973 watts. And if we are to put the cursor here at the very end, this is the average power with a value of 556.801. So next, we're going to trace the average power absorbed by the DC voltage source. So to do that, type the trace expression AVG times W times VDC. So here, as you can observe, the green waveform is the voltage power absorbed by the DC voltage source. So as you can see, there is a peak value of 1.824 kilowatts, and at the true power or the average power, 1.087 kilowatts. The results from the waveform average power absorbed by the resistor and the DC voltage source show that this part of the experiment, the average power absorbed by the resistor and DC voltage source, it was observed that both of the waveforms did not start producing power at 0 seconds. This is because the half rectifier circuit uses an RL source load where power is supplied from a DC source to an AC source. Given that these components are loads, there is no conduction unless the diode is on. Speaking of the diode, let's add another trace to see the effect of the diode in the circuit. So to do that, click on trace, add trace, and click this expression, which is the voltage across AC. And as you can see here, this dark blue waveform is the voltage across the AC. Add another trace. Let's add the voltage across the DC here. Click OK, and then you can see uh, this yellow line here. And this is the voltage across the DC, and as you can observe, it can be observed that the diode is off and there is no conduction when the value of the voltage across the AC source is less than the value of the voltage across the DC source. In relation with the average power results earlier, it can be observed that the only time where conduction of power in both components happens or turns on is when the AC voltage source is equal to the DC voltage source. This is the alpha observed in the figure 3.5. It was observed that it can be achieved when AC and VDC is equal. Since we're talking about the alpha, let's add another trace so we can observe the, for the beta. So this is the trace expression, average times power times the inductor. So we need to call out the waveform in the inductor as observed in the power of the induction waveform. The pink one, it shows a completely different waveform from the resistor and the DC voltage source average power. The endpoint of the peak waveform is the beta. The results for the first part of the experiment for the RL circuit shows that when the voltage across AC is less than the voltage of the diode, it will remain to be turned off. The time where the voltage across AC is equal to the voltage across DC, this is the time where it can be observed that the average power absorbed by the resistor and the DC voltage source will then increase. So for the second part of the experiment, this is a circuit with a inductor and a source load only. So as you can see, um, I'm, I removed the resistor. So the simulation profile is just the same as the previous one. So we're just going to run the application. And here, um, we are asked to perform transient analysis and determine the RMS current and power absorbed by the DC source. So to do that, what we should do is add trace. So adding the trace expression for the RMS current, we can see here the waveform. So if we are to check for the peak values, it has a peak value of 29.276 amperes and a true value or an average value of the current is 23.2. So now let's add the trace to check the power absorbed by the DC source. So here's the output of the waveform, checking for the value of the for the peak value. We can see that it has a value of 4.41 kilowatts. It can be observed that the half-wave rectifier used inductance to limit the current. Selecting the or adding the traces for the AC and DC, just like from the previous experiment, we can observe that we have a value of 100 for the VDC and 91.179 for the AC. Here, repeating the observation done in the first part of the experiment, it is observed to have similar results. It can be seen that the diode turns on when VAC and VDC are equal. It was observed that the RMS has a value of 23.2 amps. So if we are to check for the power across the voltage, the power of DC source started to rise after the diode turns on, and it turned off when the waveform reaches 0, as you can observe from the waveform here. So here, if we are to add the average power of the inductor, we can observe this pink waveform here and this yellow waveform here for the average power of the inductor. It can be observed that they almost turned off at the same time. So when we are to add the average power across the voltage DC voltage source, when we are to check for the average power here, we can get a value of 1.5855 kilo. In this part of the experiment, it was observed that in an ideal condition, with ideal components, the power absorbed in the source might be the same power that will be absorbed in the DC source. In the experiment, there were loss or difference in the expected results since it did not use ideal conditions with ideal components. Adding another trace to check the similarity of the waveforms is the voltage across AC, and as you can observe, the voltage across AC and the voltage of average of DC ended at the same point. So next, we are to check for the average of the VAC. So here you can observe that this needs to be changed. So if you are to change this, we're going to left click here and change this to negative. And there it went to the positive side of the plane. So if I'm to navigate through the end of the waveform, we can see these results. Navigating through the end of the waveform, it can be observed a huge difference in the values of the VAC average and the VDC average, because we are experimenting or operating in an ideal condition and not an ideal one. Conclusion: using the PSpice application, the results of the experiment showed the concept of an RL source load and inductor source load circuit. It was observed that the design of the circuits only operates when the value of the voltage across AC and DC are equal and off at all times when they are not. The concept of the inductor and DC source load shows that it limits the current through the presence of the inductor, and this results for the equal power of value of the inductance and power supply. Also, the concept of using ideal conditions affects the losses in the circuit. Since non-ideal conditions were used in the experiment, losses were observed. For the recommendation, possible errors encountered in the experiment might be present on the simulation and collection of data from the ORCAD application. Before conducting the experiment, it is essential to have a knowledge on the applications and the concepts of the topic.